Today, we're diving into a paper that I think represents one of the biggest architectural leaps in AI reasoning we've seen all year.
Oh, absolutely.
It's called Long Horizon Reasoning Agent for Olympiad-Level Mathematical Problem Solving. And it goes right after the most fundamental problem for these large reasoning models, or LRMs.
The context length bottleneck.
Exactly, that hard wall that even the best models hit at, 64K or 128K tokens?
Right. And for the kinds of problems they're targeting here, like from the International Mathematical Olympiad, the IMO, that's just not enough, not even close. You need a massive scratch pad for that kind of work.
So the goal is to let the AI just keep thinking, keep building on its own work way past that physical limit. And their solution, Intern S1MO, is, well, it's a really clever pivot.
It really is, because it's not just a bigger model. Intern S1MO is a multi-agent system, and it's built for this kind of sustained thought. It uses what they call multi-round hierarchical reasoning, plus this new lemma-based memory system.
And that's what gets it past the token limit.
That's the key. It effectively gives the agent an exploration space equivalent to something like 512K tokens. It breaks that linear constraint.
Okay, so let's touch on the innovations that get it there. You have these specialized agents, a reasoner, a summarizer, and a verifier, all working in concert.
Like a small research team. Yeah.
And it's all fine-tuned with a custom reinforcement learning framework, OREAL-H, which is a big deal in itself.
It is, and the results really tell the story. Intern S1MO is now state-of-the-art. It's beating models like Gemini 2.5 Pro on benchmarks like HMLT 2025 and AME 2025.
But the headline is the Olympiad performance.
Without a doubt. On the IMO 2025 non-geometry problems, it scored 26 out of 35 points. That officially matches the threshold for a human silver medalist.
Wow.
And in an official run at the Chinese Mathematical Olympiad, the CMO, it scored 102 out of 126. That is comfortably in the gold medal range, graded by human experts.
That sets the stage perfectly. So let's start by really defining this problem, the context bottleneck, and why it's such a wall for these ultra-hard problems.
Okay, so think about where current LRMs are successful. They're actually pretty good at AIM-level problems. Those are tough, for sure. But they're often solvable with techniques we know, like chain of thought or RL, with verifiable rewards.
Because the solution path, more or less, fits inside that context window.
Exactly. But the IMO is a whole different ballgame. Demands real depth, sustained effort, and exploring a lot of dead ends.
And the context needed for that just explodes.
It increases exponentially. The authors did a great job quantifying this. If you look at Figure 1A in the paper, they estimate that a single National Olympiad problem takes a human about 1.5 hours of pure, focused thinking time.
Okay, and in token terms, what does that hour and a half of human thought look like?
That's the kicker. They estimate that cognitive load is equivalent to processing around 512,000 tokens.
So you're asking a model that maxes out at 128K to solve a problem that requires 4 times its available memory.
You see the problem immediately. And that's why all the previous attempts at this, even clever ones with multi-round interactions or self-reflection, ultimately failed.
Because they were still trapped in a single reasoning cycle.
Right. They could reflect on their work, but they couldn't truly build cumulative knowledge across separate attempts. It was like wiping your memory clean every time you turn the page.
And what about the other approach, the formal language systems, like automated theorem provers? They don't rely on context as much?
True, but they basically swap one huge problem for another. Formal systems are structured, yes, but they have insane search overhead and computational costs. Plus, just translating a natural language math problem into formal logic is a massive error-prone task in itself.
So the solution had to be architectural. It had to mirror how a human actually solves these things, breaking the problem down and remembering what you've already proven.
That's it. Intern S1MO is designed for what the paper calls unlimited exploration capability. That's the core idea. The solution isn't one giant thought. It's a series of smaller, verifiable thoughts built on top of each other.
Okay, let's get into the weeds of this architecture then. Figure 2 shows the workflow. You have the reasoner, the summarizer, and the verifier. The reasoner is the LRM doing the actual math, but where does this persistent memory come in?
That's the lemma memory management system.
Yeah.
It is absolutely central to the whole thing. The system works in rounds. So after the reasoner does a single round of thinking, a long chain of deductions, the summarizer agent steps in.
And the summarizer's job is to act as the chief editor, right?
Essentially, yeah. It takes the entire messy reasoning history from that round, all the mistakes, the good ideas, the dead ends, and it compresses it all down into clean, validated intermediate conclusions. They call them sub-lemmas.
But hold on, if the summarizer is also an LRM, how do you make sure that compression process isn't introducing its own errors? Or filtering out something that seems minor but is actually crucial later on? That feels like a big risk.
A huge risk. And that's where the verification agents are so important. Before any of these sublemmas get stored, they get checked. But once they're verified, they go into this structured external lemma library. You can think of it like a shared notebook for the agents. Only proven facts get written down for everyone else to use.
I see. So in the next round, the reasoner doesn't have to rederive everything. It can just pull these validated conclusions from the library.
Precisely. It doesn't waste its precious context budget on things it already knows. It's like resource management for thinking. It can dedicate its current window to making deeper, newer deductions.
And for that to work, that memory has to have extremely high integrity. You can't have errors propagating through the round.
Exactly, which is why there are two different verification layers. The first one is the theorem verifier.
Okay, what's its job?
Its job is to check each individual sublemma before it gets added to the library. It uses parallel sampling. It runs 4 separate verification checks to compute a confidence score. Only high-confidence conclusions make it in.
And then you have the final check on the whole proof structure. That's the process verifier, or OPV.
The OPV is for the final assembly and refinement. So in the last round, the complete solution goes into this modification loop. The verifier gives feedback in natural language, literally pointing out the index of a logical fallacy or a gap.
And the reasoner tries to fix it.
Yep. That loop can run up to 8 times. It's just like a human getting peer review, finding a mistake in their proof, and then going back to correct that specific line.
There's also this fascinating detail about the training. They train the LRM not to rush to a half-baked answer when it runs out of its budget for a round.
Yes, instead it's trained to output partial deductive progress.
That's such a critical behavioral tweak.
It is, because it aligns the agent's immediate goal with the system's long-term goal. The architecture gives it the ability to think for a long time, but the training teaches it to be disciplined, incremental, to stop and write down a useful finding before moving on.
Which brings us perfectly to the training itself. The architecture is one thing, but you have to teach the agent how to use it effectively. Let's talk about OREAL-H, their hierarchical reinforcement learning framework.
So the foundation here is that they model the whole reasoning process as a hierarchical Markov decision process. You have high-level actions like extract a lemma or run the verifier, and then you have the low-level action of generating the next token. And the goal is to maximize that final sparse reward.
Oh, but that's the classic problem with RL in complex tasks, isn't it? The reward is too sparse. You only find out if you were right after an hour and a half of work.
Exactly. Standard RL just can't handle that. So OREAL-H makes 2 really critical adaptations. The first is progress conditioned advantage via lemma dependency graphs.
Okay, so they need to assign credit to all those intermediate steps.
Right. And instead of doing a full computationally insane Monte Carlo tree search, they do something more clever. They build a lemma dependency graph by looking at multiple attempts on the same problem. This graph basically maps out which intermediate steps, which lemmas, are most likely to lead to a successful final proof.
So the graph becomes a kind of cheap, efficient substitute for a full MCTS. How does that translate into a value for an intermediate step?
They backpropagate the value recursively. So the value of a single lemma isn't judged on its own. It's calculated as the expected final reward of all the subsequent lemmas that depend on it. This creates a much denser, more meaningful reward signal.
And that lets them optimize the policy. The agent learns to take the step that leads to the most promising path on that graph.
That's it. It's optimizing for the most promising direction, not just the final outcome. It's a huge step. And the second adaptation is just as clever. It's called Conjugate Reward Modeling for Noisy Process Verification.
Let's unpack that. This is about dealing with the fact that the verifier isn't perfect, right?
Exactly. So the process verifier might run 4 checks on a final solution and say 3 of them passed. If you just use that 75% score as your reward, your training can get really unstable because that verifier can have flukes, false positives, or false negatives.
You need a way to smooth out that noise.
You do. And they use a Bayesian approach to do it. Instead of just taking the 3 out of 4 ratio at face value, they model the hidden, latent quality of the proof as a probability. They start with a totally open mind, a uniform prior, and they only update their belief about the proof's quality based on the evidence from the verification checks.
I see. So after seeing 3 successes in 4 trials, they update their confidence that the solution is actually good.
Yes. And The reward they define is really smart. The reward isn't just that confidence score. It's the probability that the current solution's quality is strictly better than a baseline, completely invalid solution one that would fail all the checks.
So it's a probabilistically calibrated reward that filters out the spurious signals.
And that leads to much more stable learning, even when your supervisor, the verifier, is itself imperfect.
That's an elegant solution. So this combination of the architecture and this learning framework is what produced these results. Let's circle back and finish up with the experimental results and that Olympiad performance.
Right. So as we said, the inference benchmarks are SOTEP, 95% on HMMT, 96.6% on AIM. It handles the fundamentals. But the Olympiad results are what really prove the long horizon reasoning.
Let's hit that IMO score again. 26 out of 35 on non-geometry problems.
Which surpasses the human silver medalist threshold of 21 points. It's a huge achievement. The problems it couldn't fully crack, they hypothesize, are the ones that require that spark of insight, that bit of creative construction that's hard to find with systematic search.
But the head-to-head comparison with other LRMs on these really hard problems is just staggering. The Chinese National Olympiad scores.
Yeah, look at that. Intern S1MO gets 232.4 out of 260. Gemini 2.5 Pro gets 157.5.
That's a 75-point gap.
It's a massive delta. And it's a direct measurement of the advantage you get from this architecture on truly difficult problems. It's not a small improvement. It's a different class of performance entirely.
And the official CMO participation really seals the deal.
It does. That was under real competition rules. 4.5 hours a day. Human graders. The agent scored 102 out of 126, which blew past the gold medal cutoff of 78. It got full marks on 4 of the 6 questions. It's not just replicating human patterns. It's exploring complex proof paths that might even be novel.
And we know this is an architectural win, not just a matter of scale, by looking at the ablation study.
Absolutely. Table 2 in the paper shows it perfectly. You add in multi-round reasoning, performance jumps, you add in the OREAL-H training, performance jumps again. The gains come directly from the structure and the smart learning signal.
And to really hammer that point home, there's a smaller version, Intern S1 Minimo.
Right, a parameter-efficient variant. And even that smaller model still outperforms Gemini 2.5 Pro on the CNMO. It shows that in this domain, a better architecture really can trump raw parameter scale.
So what's the big takeaway here?
The big takeaway is that to reach true mastery in a domain like this, you can't just keep making models bigger. You need a structured, verifiable cognitive architecture. You need something that can support sustained, multi-step deduction, which is exactly what this system provides.
It's just incredible to think that we have an agent that can solve problems requiring a human to sit and think for an hour and a half straight. So here's a final thought for you to chew on. If this combination of lemma-based memory and verified multi-round reasoning is the key to cracking long-horizon math problems, what's next?
Where else can it be applied?
Right. What about applying this exact architecture to non-mathematical scientific discovery? Think about materials science or theoretical physics. Fields where managing context and building on proven intermediate results is just as much of a bottleneck.
That could open up completely new ways to accelerate research. A fascinating thought.
That concludes our deep dive into the long horizon reasoning agent for Olympiad-level mathematical problem solving.